In this video, we would like to introduce our work, Fully Asynchronous Neuromorphic Perception for Mobile Robot Dodging with Loihi Chips. Sparse and asynchronous sensing and processing in natural organisms enable ultra-low latency and energy-efficient perception. Inspired by the biological silicon retina, event cameras offer advantages such as high temporal resolution, high dynamic range, and low power consumption. However, utilizing sparse and asynchronous event streams remains a significant challenge. The traditional processing paradigms, e.g., event frames, 3D voxels, encounter issues such as feature loss, event stacking, and high computational burden. These problems deviate from the intended purpose of event cameras. Inspired by biological neurons, spiking neural networks share many similarities with event cameras. Building on this synergy, we propose a fully asynchronous neuromorphic paradigm that integrates event cameras, spiking neural networks, and neuromorphic processors. In the work, we use two-state leaky integrate and fire spiking neuron model based on voltage and current to construct spiking neural networks. The proposed method is divided into two stages, offline training and online inference. The following sections provide a detailed introduction to each part. In offline SNN training with CPU/GPU simulation, we define the loss function as the difference between the actual spike count and the desired spike count for each channel. Subsequently, the proposed fast loss backpropagation method is employed to update the weights. In online inference with Loihi chips, we establish a mapping relationship between events and neurons to enable asynchronous processing. The weights of Kapoho Bay are integer quantized from the simulated SNN. Finally, the spike output trains are mapped to the corresponding dodging direction and speed. Finally, we show our fully asynchronous neuromorphic system including the host computer, Kapoho Bay, and mechanism wheel chassis. Our system process events asynchronously and dodge successfully. We set up comparison schemes from representations and networks. Then, we compare the performance of EFANN, ESTANN, EFSNN, and our method with different time windows, 30, 50,100, under indoor normal lighting. The results demonstrate that both ESTANN and our proposed method exhibit strong robustness across different time windows. Next, we select the best model of each scheme to evaluate dodging success rates, with different lighting conditions and objects. Experimental results show that the dodging success rates of EFANN and EFSNN decrease significantly, 3.62% and 7.5%. Then, we analyze the effect of the proposed Key Event Point (KEP) module. The results indicate that the success rate remains largely unchanged before and after implementing the KEP module. In terms of average points, the results indicate that, following the implementation of the EKP module, only 29.9% of the ball events and 17.49% of the human events are utilized. We then visualize the event streams before and after applying the KEP module using the event frame method. Our EKP module retains the object's clear edge feature and effectively removes background noise. Finally, we evaluate the power consumption comparison of the following different schemes on different devices. The inference power consumption of our method is only 0.95% of that of ESTANN on the GPU. Even in the energy-saving mode of NVIDIA Jetson NX Orin, our method consumes only 4.3% of the power used by ESTANN. Additionally, compared with EFSNN, our power consumption is reduced by 98.36% on the same neuromorphic processor. The following section presents the dodging performance of our method in real-world scenarios. First, we demonstrate the performance of our asynchronous method in dodging under different lighting conditions using a ball. Then, we demonstrate the performance of our asynchronous method in dodging under different lighting conditions using a human. The results show that the proposed methods can dodge successfully in different lighting conditions and objects. Next, we compare the dodging performance of the proposed method with other schemes under different time windows and in indoor low-light conditions. The results indicate that both ESTANN and our method demonstrate strong robustness across various time windows and in ultra-low light conditions. Notably, EFSNN exhibits significantly longer processing times. Our specific contributions are follows. Thank you for your watching.